Okay, now let's get back to the chapter we have. So chapter 4, as we said, we need to talk about the second law of thermodynamics, but in order to understand the second law of thermodynamics, we have 4 concepts we need to understand first. Last lecture, we started with explaining reservoirs. So large area, it can supply heat, it can absorb heat, but the temperature of itself, it will not change. So this is the reservoir. The second concept, we explained reversibility. So we said reversibility, this is a theoretical process. There is nothing like operates in a reversible way in actual life. Okay, but reversibility, it describes the way that the process can take place with very small driving forces, very long times, the maximum efficiency that can be obtained from this one. When we described last lecture, we solved 2 examples. One was an application of reversible process, irreversible process, and we ended up with this conclusion that if you need to calculate Q, the amount of heat, if you need to calculate O, the amount of work for reversible and irreversible process, they are not the same. Okay, so the question why we are studying reversible process, these are not actual, these does not exist, so why we like keen on understanding and analyzing them? The first thing, they are easy to analyze. Reversible process, we don't have frictions, we don't have losses, so it's easier to analyze the reversible process. The second thing, this is an ideal approach of any process. So if you need to analyze any actual process, we need to know what is the maximum efficiency that this process can operate, what is the maximum performance of this process. Okay, and the maximum performance can be obtained if you assume that this process operates in a reversible manner. Make this easy calculations, calculate the efficiency, or calculate the work, calculate the heat, and the numbers that you can obtain from this reversible analysis. Then you can like consider them. This is the maximum number you can achieve, and this also can be a double check in your solution. For example, so if you are studying efficiency of a process, reversible process, and let's say the efficiency is 60%. Then you are analyzing of the actual process and you find the efficiency is 70%. Now you are sure that there is a mistake in your calculations, because when you make the analysis, assuming reversible behavior, the efficiency was 60, this is the maximum. Okay, this is the ideal or performance of this process. Okay, so this is why we are using reversible process as a guidance in our analysis for our actual process. The third point we need to describe is heat engines. Again, let's recall the first one. When we started talking about the second law of thermodynamics and said the second law of thermodynamics is important because it complements the insufficiency of the first law. First law of thermodynamics says if you have work, so this work can be converted into heat. So if you have work here and you have this motor rotating, so the temperature here will increase. Or if you have water and you start to increase the temperature of this water, this motor will start to rotate. This is the first law of thermodynamics. Okay, but second law of thermodynamics, this cannot be happen. If you have work, work can be converted into heat. But if you have heat, heat cannot be converted into work. This is the second law of thermodynamics. So the question is, can we have a device, this device convert heat into work? And the answer is yes. We can have special devices. These devices are called heat engines. So these heat engines can help you that if you have heat with these devices, with these heat engines, this heat can be converted into work. And by these devices, you can obtain work from heat. Clear? Okay. So this is the whole idea of heat engines. It's called work-producing devices. These devices produce work, and the input of these devices is heat. So what is the working principles of these ones? So heat engines basically are associated with high temperature source, which is high temperature reservoir, low temperature sink, reservoir sink, and then we have something moving between the source, the heat engine, the sink, and then get back to the source, heat engine, the sink, and this is called a working fluid. So heat engines, you have fluid, it's called working fluid. This working fluid is keep moving between heat source, components of the heat engine, heat sink, and then go back, source, heat engine, sink, then go back, source, heat engine, sink. This reminds you of a cycle process. So heat engines are cyclic. We We start at some point, we have a whole cycle, we return to the starting point. We have another cycle, we return to the starting point as one more time. So the main features that you will see in all heat engines we have, so we have working fluid. This working fluid starts at the high temperature source, it gains temperature, it receives heat from this source. Then it converts part of this heat into work through the heat engine. We will explain the components of the heat engine later. Then we will have the working fluid. It will come to the sink, reject any waste of heat to this low temperature reservoir sink. And then we have cycle, it returns back to the source, receive heat, go to the engine, produce work, any waste heat, reject it to the sink, and go back to the source and complete the process. Okay, so if this is the diagram of the the heat engine, so what actually we have in the heat engine? This is a picture of the actual components we have in the heat engine. So heat engine, we have 4 components integrated together. We have pump, we have boiler, we have turbine, we have condenser. The boiler, this one can be considered at the high temperature source that we have. The condenser we have here, this is the one can be considered as a low temperature sink. And if you can see the same thing, so the working fluid go to the boiler where he can absorb heat. You can call it QN, amount of heat added to the working fluid. Then this working fluid will go to the turbine to produce work. Then from the turbine it will go to the condenser to release the waste heat. Then it will go to the pump just to adjust its condition to return it back to the initial condition and complete the cycle and return it back to the boiler. So we have the working fluid moving from the boiler, turbine, condenser, pump, and repeat. Boiler, it gains heat. Turbine, this is the stage that we are obtaining work from this one. So we have QN. Part of this QN will be converted into work, and any remaining heat, this will be rejected as the condenser. And again, cycle means we need to return the working fluid to the same as initial condition. So to return it back, we have pump here to increase the pressure to the same as initial condition and complete the cycle again. Clear? Any questions? Okay. So this QN that is added in the boiler, this is the same as QN we said. It will go to the working fluid from the high temperature source. Q out, that the heat rejected at the condenser, this is the same as Q out we mentioned here at the low temperature sink. Here we have something that Q out is not equal to 0, but here we have in the simplified diagram we said we have net work. But here we have something called work out, we have something called work in. Okay, so we have relationship between them that they are not the same. Oops. These are not the same, and this network is work in, we have minus work out. Okay, so just to make sure that the comparison between them. So the network we have in the simplified diagram here, this is just the difference between the work in we add to the pump and the work out we obtain from the turbine. Okay, clear? Is this concept clear? Okay, so if we return back, do you remember when we explained Kelvin Planck statement? So Kelvin Planck statement, he said, second law of thermodynamics, it's impossible for any device that operates in a cycle to receive heat from a single reservoir and produce a net amount of work. If we put this description on a diagram, this is what Kelvin Planck said. Kelvin Planck said if you have high temperature reservoir and you have a working fluid, it's impossible that you have a working fluid that will obtain heat or receive heat from this source, and all of this heat will obtain as work. So this is the schematic of this description. He said this is impossible to have. You should have heat rejected to a lower temperature sink. Okay, but if you don't have this thing, so the whole process is impossible. Then the other statement, Clausius' statement. Clausius' statement says it's impossible to construct a device that operates in a cycle and produce no effect other than the transfer of heat from a lower temperature body to higher temperature body. So let's put it on a diagram. So what Clausius said? Clausius said if you remember the heat engine, here in the top we have high temperature source, and here at the bottom we have low temperature sink. Clausius said you cannot flip these reservoirs. So you can say we have low temperature sink. This low temperature sink that you can give heat to the working fluid, then you can obtain work, and the amount of waste heat you will reject it to a high temperature source. This is also impossible. So the correct one that you have high temperature source at the top, not low temperature sink. You have low temperature sink at the bottom, not high, not nothing, and then you have the working fluid will receive heat from the high temperature source, produce some work through the turbine, and any heat waste will be rejected to the low temperature sink. Clear? Okay. So some important terms. Here this slide, it gives you a description of everything we have. Qin, the amount of heat supplied to the working fluid in the source, in the high temperature source. Q out, this is the amount of heat rejected from the working fluid to the sink. Work out, amount of work delivered by the working fluid as it expands, the amount of work obtained from the turbine. Work in, amount of work required to compress the working fluid in the pump. And net work, this is the net work output of the heat engine, which is the difference between inlet work and outlet work. Okay, so this slide this is the definition of every term you will see in the problems, every term you will see in this chapter, even next chapter. All of these terms will be repeated by this time. Okay, and this is the equation we have for calculating the network. So network can be obtained from inlet work, outlet work, or even can be obtained from the inlet Q and outlet Q. See, any of these equations posed in the given, you can use to calculate the network that you obtain. Clear? Okay, so let's recap. So we have devices called the heat engines. These are cyclic, so we have working fluid return to the same initial condition and complete the cycle. These are called work producing devices. So the objective of this device, use heat in order to produce work. Okay, from these devices we can now understand what Kelvin-Planck statement means, what Clausius statement, description of the second law of thermodynamics means. So in this one you have high temperature source, give heat to a working fluid. This working fluid go a turbine, produce work, then go to a condenser, reject any remaining heat. Then you have pump to return it to the same as initial condition, compress it, and complete the cycle again. Any questions? Good. Okay. Anyone start writing? The fourth concept that we need to explain is the thermal efficiency. Thermal efficiency of heat engines. So again, this is the description of the heat engine we have, and as we said, the ultimate goal of the heat engine is to convert heat into work. And this Q out, this one, is not equal to 0. So this means always we have some waste heat we need to reject. So this means the efficiency is not 100%. So even if you see the question in MCQ question, can we have 100% heat engine? This is no, we can't have 100% heat engine because always you will have waste heat. This is the statement of the Kelvin-Planck. Always you will have waste of heat that you will have. So since we have waste heat rejected to the low temperature sink, so we must account or calculate something called thermal efficiency. And what is the thermal efficiency? Efficiency in general is what you need to obtain, the output, divided by the input, what you are giving to this process. So if you have this diagram, so we have Q in, we have net work, we have Q out. What is your desired? So do you think you are designing this device to obtain Q in, or to obtain work, or to obtain Q out? What is your desired output? Work out, okay? It's called work producing devices. So the output is the work. This is the output we have. And what you are like giving as input to this device in order to produce work, Q in or Q out? Q in. So this is your input. So I have device, I give this device heat, and from this heat, device can produce work. Okay. Thermal efficiency is the ratio between the amount of work that you are obtaining from it and it's the net work. Again, so this is net work, not work in, not work out. Okay, so the efficiency is the net work out. Okay, the like difference between work in and work out, difference between Q in and work out, divided by the Q in, the total heat in. From first law of thermodynamics, if we apply the energy balance equation, then we can say work net is Q in minus Q out. So you can substitute it in the equation and we can say efficiency is Q in minus Q out divided by Q in, or it's 1 minus Q out over Q in. All of these ways you can use. So you can use this formula to calculate thermal efficiency, or you can use this formula to calculate thermal efficiency. Any one of them based on the given information you have. If you have Q in, Q out given, so use them directly, calculate efficiency from this formula. If you have network given, for example, if you have Q in, then use the first one to calculate it. Okay, so you have two mathematical ways that we can use to calculate the thermal efficiency. Okay, so this is the equation we have. Other textbooks, and this one just to give you an idea what you can see if you like Google some information on the internet. So some textbooks, they didn't use Q in and Q out, but instead of that, they are using QH and QL. Okay, so QH, this one is the amount of heat that's received from the high temperature reservoir. So this H here, so this H here indicates to high temperature. And this L here represents the amount of heat received by the low temperature reservoir. And this is representing Q out and Q in. So this Q in, this one here in the heat engine is QH, Q out in the heat engine, this is QL. So if any amount of heat like received or gained from high temperature source, this some websites, some textbooks, they use the subscript H. And if it's from the low temperature reservoir, they use its L. So some textbooks, you can see the thermal efficiency 1 minus Q out over Q in, or 1 minus QL over QH. This is the same. Okay, just I put them to you because I figured out some students were confused previous semester when they read this information. They were confused what is the difference between QL, Q out, QH, and QN. So basically they are the same, just different ways to explain it. Okay, so if you see any one of them, so this is fine now. Now let's take example. Here we have heat is transferred to a heat engine from a furnace at a rate of 80 megawatts. If the rate of waste heat rejection to a nearby river is 50 megawatt, determine the net power output and thermal efficiency of this heat engine. So according to this one here we have heat transferred to a heat engine from a furnace at this amount. So this number represents Q in, represent network, or Q out. What do you think? It's Q in. This one, the amount of heat added to the working fluid. So it said it's transferred, heat is transferred to a heat engine, like from a furnace. So this furnace, this is high temperature source, and he says we have this heat is transferred to the heat engine, to the working fluid of this heat engine. If the rate of waste heat rejection to a nearby river is 50 megawatt, so this number represents what? Q. This is Q out or QL. Okay, so we need to find the thermal efficiency. So here we have this example here. So we have QH is 80 megawatt, QL is 50 megawatt. So you can calculate thermal efficiency, and even you can calculate net work. So from first law of thermodynamics, we know that network, this is Q in minus Q out. So network will be 80 minus 50, so this will be 30 megawatts. And this is the first requirement. Okay. Second requirement, we need to calculate efficiency. So efficiency is 1 minus Q out over Q in or net work divided by Q in. Now we have all the numbers. You can use any of these formula. But if you have, this is like a tip for the exam. If you have like two formulas for an equation, similar to this one, to calculate thermal efficiency, for example. So we have this formula you can use, and you will substitute in this formula with given information. Because Q in, Q out, both of them are given. We can also use this formula, but this formula we have net work. This one we calculate. Here I know that the calculation of net work is very simple, so there's no chance to have any mistake in this. But sometimes if you have like two mathematical formula to calculate anything, and one of them it have like variables or properties that all of them are given, and the other one contains any property that you calculate, personally I prefer to go with this one. Because just in case if you have any mistakes in the calculation, then this will have mistakes in the other one. Okay, so always keep this in mind. If you have any way that based on the given info, just use it. So if we have this one, so this will be 1 minus 50 over 80. So, and if you make this calculation, the efficiency will be 0.375, which is equivalent to 37.5%. And this is the second requirement. Clear? Any questions? Okay. Let's see another problem. Here we have car engine. This car engine with a power output is 65 horsepower. So this is power output. So this number represents what? Workout. So this term represents the net work we have. It has thermal efficiency of 24%. So we have here thermal efficiency is given. Determine the fuel consumption rate of this car if the fuel has a heating value of 19,000 BTU per pound mass, which means if you burn 1 pound mass of this fuel, you will obtain this amount of heat. So we need to calculate the fuel consumption rate, the mass flow rate of the fuel that we need to burn in this engine. So again, let's see the information we have here. So we have given thermal efficiency is 24%, which is 0.24. We have net work is 65 horsepower. Also we have heating value. This one is 19,000 BTU per pound mass. These are the given information. If you recall chapter 1, we have horsepower. This is one of the units that we are using to describe power. BTU, one of the units used to describe energy, and they are not consistent. So we need to convert one of them to the other one. So the easiest thing is to convert horsepower into BTU. So this would be the first step. We need to convert the horsepower to BTU per hour. And we know that if you check the conversion factor, we know that 1 horsepower, this one equal 2545 BTU per hour. Then according to this, we can say the net work This one will be 65 times 2545 BTU per hour. Then we have efficiency is net work divided by Qn. So we know that efficiency we have is 0.24. The net work we have is 65 times 2545 divided by Qn. So we can use the thermal efficiency equation to calculate the input heat to the system. That will be 689 like 270 BTU per hour. So this is the Qn that we need to add to the engine, okay? And we have the heating value for this engine is this number. So what is the amount of fuel that we need to burn to give you this Qn? Okay, so we know that Qn ultimate. This is the ultimate amount of Qn that we need to obtain. This amount can be obtained by burning like amount of fuel. And the requirement is what is this amount of fuel. If you check the units, this is BTU per hour, this is BTU per pound mass. Okay, so how you can convert them? So we have Qn, which is BTU per hour. This is equivalent to heating value, which is BTU per pound mass times mass flow rate in pound mass per hour. So if you have this one, then you can say that pound mass will be cancelled with pound mass and the remaining will be BTU per hour, which is here, BTU per hour. This is part clear? So you have some amount of fuel, you know the amount of fuel, you know the heating value of this one, multiply both of them together, and this multiplication should equal Qn, the amount of heat that we need in this car engine. So we have this number, 689,270 equal heating value 19,000 times mass flow rate. Then if you substitute in the equation, you can see that the mass flow rate is 36.3 pound mass per hour, and this is the consumption rate that we need. So every hour in this car, we will consume 36.3 pound mass of the fuel. We will burn this amount of fuel. If you burn this amount of fuel that has 19,000 as the heating value, then you will obtain the Qn value that you need for this car engine. Clear?